last section of notes is looking at temperature and rate, and then we're going to be looking at activation energy and how we can relate the activation energy of a reaction to the kinetics constant that we have been calculating the last couple of days in class. So first, I just want to remind you of the collision model. It was in the very first video of this unit that I asked you to watch, but just as a reminder, the collision model has three postulates, the first one being that molecules actually have to collide in order for the reaction to happen. And when the collision happens, they must collide with sufficient energy, so the molecules must hit hard enough that the bonds will actually break. And then the last one is that when the molecules collide, they have to have the right orientation, or they have to be lined up in just the correct way. Remember from the kinetic molecular theory last unit that the temperature of a reaction is related to kinetic energy. So all reaction rates are going to increase when temperature increases, because if the molecules are moving faster, then they're going to collide more frequently, and there's going to be a larger fraction of collisions that have enough energy. So that's why when you increase the temperature of a reaction, the reaction rate is also going to increase. And earlier when we talked about the collision model, I had mentioned they have to have sufficient energy, and again, that sufficient energy is called activation energy. The symbol that we often use for activation energy is that E with a little subscript A. So when you see that, remember that that is the activation energy. This is just a model of a reaction happening, so you can see the collision model. And so if the molecules collide and no new products form, that means it requires more energy. And in order for the bonds right here to be broken, the molecules have to hit with the correct orientation, and they also have to hit with enough energy. So for example, if you look at the picture in letter A, the bromines are colliding, so that must be the correct orientation. Whereas if you look at option B, when the oxygens collide, that's not the correct orientation for this particular reaction, which means there's not going to be a reaction that happens. Again, these reaction diagrams were also reviewed in the first video, so make sure that if you don't know how to label a reaction coordinate diagram, that you go back and watch that first video, because you will have to do this on your test. And so you will have to be able to label one of these diagrams, whether it's a forward reaction or a reverse reaction. And so make sure you go back and look at that. Again, the activated complex, or the transition state, is the unstable reaction intermediate, which we talked about last week. And so this part at the very top of the reaction diagram is called the activated complex, or the transition state. And Arrhenius was a chemist who postulated or came up with the idea that the number of collisions having enough energy has to be equal to this reaction, or this equation at the bottom. And so the number of collisions times the E function, so the exponential function, and then that's raised to the negative EA divided by RT. And so this EA here is the activation energy, and temperature is T, and then we're dealing with energy, and so the R constant that you're going to use is the 8.314 R constant. This is not really an equation that you're going to have to do a lot of calculations with, but it's just showing you that the number of collisions that are going to have enough energy is related to the activation energy and the temperature. So again, this is not a calculation that you're going to have to do, but you should have an idea that Arrhenius did come up with an equation to figure out how many collisions in a reaction are actually going to be successful. In order for, again, this is just repeating what we did earlier. So in order for a reaction to collide, there are two requirements. They must have enough energy, and they must have the right orientation. Taking these two factors into account, you can write the rate constant in this particular equation. And this equation is not the one that you're going to use. The one that you're going to have to know how to use is at the bottom of the page. But in order to get there, let me explain the first one. And so this lowercase k is just the rate constant that we've been calculating before. Z is the collision frequency, which Arrhenius came up with on the previous slide. P is just a steric factor. It's always less than 1. It reflects the fraction of collisions with effective orientations. That's not a number you're going to have to memorize or know or anything like that. And then the exponent of the exponential function is the fraction of collisions with enough energy to produce. And so because Arrhenius came up with this, oftentimes this z times p frequency, the collision frequency and the steric factor are just multiplied and replaced with the letter A, which we call the frequency factor. And that's um, what's used to calculate the Arrhenius equation. And so this here at the bottom of the page, the Arrhenius equation, is the one that you will often use and the one that you will be expected to know how to use for your test. You do not need to memorize it, but you do need to know what all the different parts mean. So again, that K is the um, rate constant that we've been looking at. The capital A is called the frequency factor, which is something that's a constant for any given equation, and it'll be given to you. And then the exponent that the exponential function is raised to is the negative activation energy divided by RT. And this T has to be in Kelvin. And because we're dealing with energy, the R is going to have to be the 8.314, not the gas law constant. All right, so if you take the Arrhenius equation from the previous slide and you can take the natural log of both sides and do some rearranging, you get this equation at the top of the page. This equation is far more commonly used than the Arrhenius equation on the back, and the reason for that is because it is in the slope-intercept form of a straight line, and so you can plot the natural log of k versus 1 over time and use the slope of that line to figure out the activation energy. And so if we look at this example, so if I give you the following data, so I have a bunch of temperatures and I have the rate constant for each of those temperatures, I can plot the natural log versus time and show you how you can use that information to figure out the activation energy of a reaction. And so here's the data. So I took the temperature and the rate constant and took the natural log of both, or of the K constant, and then 1 over temperature, and I graphed it, and you get this straight line. And so if we look at the equation for this line and compare it to the number at the top, or the equation at the top, I can figure out the activation energy for this particular type of reaction. And so I know that the slope of the line, negative 12,447, is equal to the slope, which is this at the top. So that's equal to negative activation energy over R. Your negatives cancel out, and this should always happen because you can't get a negative activation energy. The amount of energy is always going to be positive. And so then if I take this new equation and plug in my value for R, so 12,447 is equal to the activation energy over 8.314. Multiply those two numbers together, you are going to get that the activation energy for this particular reaction is 1.03 times 10 to the fifth, I believe, joules per mole. And that is how you can use the equation of a line when you graph the natural log of K versus 1 over time to get the activation energy for a particular reaction. So you don't even need to use the other form of the Arrhenius equation. Now, you may be asked, I won't ask you on your test, but they may ask you on the AP exam. Once you found the activation energy, you can go back and use the Arrhenius equation to find the frequency factor. But that would just be a matter of taking this activation energy that you found and plug it into the previous equation. While you can use the previous equation to find the activation energy, a much more common way is to use this equation. So this is, again, as it says at the top of the page, the most common way to determine the activation energy. And it's by taking the rate constant and using the rate constant for various temperatures and plugging it into this equation. Now you would have your K for one equation and your K for another equation, and then you would have your temperature for one equation and your temperature for another equation, and you can put them all into this equation and solve for the activation energy. Or you could do the example that's on the page. And so I gave you the rate constant and the temperature for one, and then I gave you the temperature of another reaction, and I'm asking you to find the rate constant at that particular temperature of 430 Kelvin. And so let's do that calculation. And so again, if the rate constant at 462.9 Kelvin is 0.52 times 10 to the negative fifth inverse seconds, determine the value of the rate constant at 430 Kelvin. And I give you the activation energy for this particular reaction. And so all you're going to do is take those values and plug them into the equation at the top of the page. That equation is not something that you need to memorize, but you do need to know how to use it. It does not matter what you choose to be your 1 and 2 as long as you match up the kinetics constant 2 with the temperature 2. And so if we just use the first set of data in the question as your 1, I can just plug in the answer. And so you get the natural log of K2, which is what we're trying to find, over 2.52 times 10 to the negative fifth. And then I'm going to set it equal to your 8.314. Now, the 8.314 unit is joules per mole Kelvin, and so we have to take your activation energy and convert it to joules. And so 160 kilojoules is 160,000 joules, and then 1 over. Now I use the 462.9 as my T1 and 430 as my T2. And so if you do this math, you get the K2 to be 1.05 times 10 to the negative sixth. And your unit is going to be the same as it is for K1, so 1 over second or inverse second. Now, I would recommend that you stop this video and try that math just to make sure that you get the same answer that I got. And if you're unsure how to do it, you can ask me in class on Monday or Tuesday, and I'll be happy to walk through the steps if you're not sure how I got K2. All right, the very last bit of the notes is just looking at catalysts, and so it's all conceptual. There's no math or anything, so I'm just going to quickly run through it. And so as a reminder, the catalyst is something that speeds up the reaction without being consumed. And we already looked at mechanisms that had reactions, or mechanisms that have catalysts. And it was something that appeared at the beginning of the reaction and then it didn't appear until the end. So it speeds up the reaction, but it doesn't get consumed at all. An enzyme is a biological example of a catalyst, and so it speeds up reactions in our body like digestion and things like that. We talked about this a little bit a couple days ago. And so how a catalyst works is it creates a temporary bond with the reactants and holds them at the correct orientation, and that allows the activation energy to be lowered and have the reaction happen faster. Now, if you remember from biology, the little lock and key analogy, and that's how catalysts work. There are two types of catalysts. You have a homogeneous catalyst and a heterogeneous catalyst. A homogeneous catalyst is something that is in the same phase as the reacting molecules. So if all the reacting molecules are liquids and your catalyst is also a liquid, that would be a homogeneous mixture. If you have a bunch of liquids and your catalyst is some solid salt that you add, then you would have what's called a heterogeneous catalyst. And so the catalyst is a different phase than the reacting molecules. The last slide in the notes looks at the 4 steps that are needed when you're looking at a heterogeneous catalysis or a reaction that involves a catalyst that is not the same phase of matter as your reactant. Now, I've never seen an AP exam that has a question asking you to describe these 4 steps. I won't ask you to do this on your test, but I did just want to show it to you so that you know that if you have a reaction that is referred to a heterogeneous catalysis, or again, when the catalyst is heterogeneous or a different phase of matter than the reactants. There is a few more steps that are involved, and that's simply because you have 2 different phases reacting. Again, I'm not expecting you to memorize this. I've never seen a question on an AP exam that asks students to describe this process, but I did want to show it to you, and so you can quickly read it and know that you are going to have a little bit extra steps if the catalyst isn't the same phase of matter as the reactant.